The advantage of looking at motion and just thinking of straight line motion means it's very useful for vectors, because vectors, of course, are straight lines. So when we get into something like projectile motion, which is what we're about to look at, which actually is in 2 dimensions, what we do is we just break it up into its vectors. We'll have a horizontal vector and we'll have a vertical vector, and then we can resolve them and get answers. So let's talk about position vectors. Just a reminder of what all these things are. Position vectors are when we join the point up to the origin. Okay, so U with the little tilde underneath is a symbol for a vector. Okay, we know that another notation for the position vector could be OP with the arrow on top. We could write it as an ordered pair. It's probably the most unusual of them all. Column vectors, they can come in handy with working out. It's not a bad way of doing it, writing it that way. And of course, if we break it into its components, we have X in the I direction, which traditionally is the horizontal vector, and Y in the J direction, which traditionally is the vertical vector. The length of the vector, again, it's just Pythagoras, square root of X squared plus Y squared. And the direction of the vector is the angle it makes with the positive x-axis. And can be worked out using trig, of course. We're going to talk about space curves. So as I was saying, all of our motion's been in a straight line so far, but obviously motion doesn't always happen in a straight line. So what we do is we consider the position vector, and it's going to be some function, right? But the scalar t is what we'll substitute in. And t will, of course, be time for our purposes when we're talking about motion. So there's our vector there. So it started to go and it's going off in that direction. Now, as t changes, so as time changes, then the position of p will change, of course. So the position of the endpoint of that vector will map out a curve depending on the motion. Right? So I could have changed over there. So plus some change in time, I could now be at Q. And then again, I could add on some more time and I might be at R. So there might be some curve. It might have travelled like this to get to those points. And obviously, if we had the equation, we'd know exactly how it all went, but possibly it did something like that. So the velocity vector, it's the same as what we've been looking at, would just be a tangent to our space curve at the particular point. So at P, velocity will be going in that direction. Okay. Now, if you want to find velocity and acceleration and all their components, we have to analyse our vectors. But really, it's no different to what we're doing, because the way we're going to analyse it is breaking it into its horizontal and vertical components. Everything becomes straight line motion, and we just do what we've been doing with motion. So displacement, it'll be some function. That's RT, that'll be the displacement vector, but we can break it up into its components. There'll be some function in the horizontal direction. There'll be some function in the vertical direction. So therefore, if we want to work out velocity, we just differentiate each of the components. And then we could find the magnitude of the velocity. Again, using Pythagoras, we can work out the size of that vector. And we can work out what direction it's travelling in by using trig. And acceleration, we'll just differentiate it again. And so same sort of thing. I want to find the magnitude. Then we can, bit of Pythagoras, we've got our answer. Particle moves so its velocity at time t is given by this expression here, whatever that curve happens to do. Given that, remember, t is the parameter, if you like, that we're substituting in. So that's basically saying initially, because we're saying time equals 0. And it's equal to I, so 1 unit in the positive direction. Find the position vector at any time. Okay? Well, dx to t, I'll just differentiate the two components. So dx to t, because remember, we've been given a velocity vector, so that's dx to t, minus 2 sine 2t. So if I want to go back to get the position vector, I'll integrate. So it's exactly the same as what we've been doing. Initial conditions were that when t equals 0, we were 1 in the horizontal direction. We want to link time and displacement. So carrying out our integration, we come up with x equals cos 2t. The difference now is we also now have to look at the vertical direction as well. What's happening there? So we'll do exactly the same thing, but now in the y direction. So the y to t would be 4 cos 2t. Now initially, we haven't got anything in the vertical direction because we said we were just horizontally 1. So when t equals 0 in the y direction, we've travelled 0. We want to link time and y together, so a bit of integration, and we get our y component. We now have the two components, so we can come up with an expression for our displacement vector. There it is, cos 2t in the I direction and 2 sine 2t in the j direction. The position vectors of particles A and B. So we've got two different particles here, so I've called them RA and RB. There's the vectors that describe the motion of our two particles. We want to prove that they will collide while travelling at the same speed, but they'll be at right angles to each other. Well, we know if they're going to collide, they must occupy the same position at the same time. So therefore, t cubed minus 9t plus 8 must equal 2 minus 2t squared. They must have the same horizontal component. That gives me a cubic to solve, which is not exactly easy, so I'm not going to do it. I'll look at the vertical direction. That looks easier right now. So t squared is equal to 3t minus 2. Verticals have to be equal as well. That's a quadratic, a lot easier to solve. So we come up with two possibilities. They might have collided at 1, they might have collided at 2. Because all we're now saying is they'll be at the same vertical height at those two times, not necessarily the same horizontal. But now all I've got to do is just check with that other equation to see which one works, and then I'll know which time it is that they collide. And when t equals 1, it's actually horizontally at -1, so that's not going to be the collision point. When t equals 2, yes, it equals 0, that's what we want, so it must be after 2 seconds they collide. So right, we now know when they collide. There's the two displacements. Let's find the two vectors. You see, whenever you're talking about the direction that the particle is travelling, you always use the velocity vectors, because the velocity is telling you the direction you're travelling. So there's the two velocities. We had to prove they're at right angles. Well, it was t equals 2, so let's work out what the velocities are. There's the first one, 3i plus 4j, and the second particle, minus 4i plus 3j, and this is where our vector work helps. Because you might recall there was a beautiful rule about vectors being at right angles to each other. There's the magnitude, 5, there's the magnitude 5. So yes, they are travelling at the same speed, that's what we wanted. But now I'll use the dot product, because we said two vectors are perpendicular to each other if the dot product was equal to 0. So let's work out our dot product. Yep, that is 0. So yes, they also collide at right angles to each other. Well, let's have a look at this idea of projectile motion then. So extension 1, two-dimensional motion in the air, subject to gravity. By the way, we're going to assume that air resistance is negligible and it's not having much effect on it at all. These are the two facts that we always start with. If something's just travelling in the air, the only thing acting on it is the force due to gravity. Because nothing's touching it, it's just in the air. So gravity. Therefore, we actually look at the forces. And that'll come more into play in extension 2. But that's what I'm basically saying here, because force is mass times acceleration. So we're just looking at the accelerations in extension 1. So if the only force is the one due to gravity, then the only acceleration that's happening is in the vertical direction. So horizontally, for this problem, there is no acceleration horizontally. So x double dot will equal 0. But vertically, minus g. So minus gj to be more correct, because it's in the vertical direction. What are our initial conditions? Well, it depends on the problem, but let us just assume it's going to go off, obviously, with some velocity, they'll tell us, and some angle to the horizontal. So here's it's convenient to use a number plane, so we're talking about x and y. We're going to shoot off at an angle with some velocity. And then there's the velocity. Bingo. We can work out the horizontal and the vertical component, because I'm not interested really at v at this point. I want to know what's happening horizontally. I want to know what's happening vertically. So using trig, we can see, well, horizontally, we'll start with v cos theta. And vertically we'll start with v sine theta. And they'll both be going in the positive direction according to my diagram anyway. But then a little bit later, it's going to change. So it's now at that point there, and it makes an angle of alpha. And then it'll get to the top, because at some point it's going to stop and come back down. So it'll get to the top and it'll look like it's going horizontally at that point. But then it will keep going, and now it's going down. And then it could hit the ground, and it'll hit the ground at a certain angle. But we get a parabola. For convenience, I start at the origin. Now, you might not always do that, because sometimes you might be projecting a white note at the top of a cliff or something like that. So you might want to make initially the vertical height equal to whatever the height of the cliff is. By the way, maximum range for a projectile will always happen when the angle's shot off at 45 degrees. We'll start with our acceleration. So we start with acceleration, but I'm not calling it acceleration. I'm saying it's the rate of change of velocity. Let's have a look at the x. So I'm going to integrate the x equals, well, it's still going to equal 0, because when I separate the variables here, 0 times the t is still 0. My initial condition was v cos theta, and I'm going up to x dot. We solved that. Surprise, surprise, x dot is a constant v cos theta. That makes sense, because remember we said there was no acceleration horizontally. So we're expecting a constant number for velocity then, because there is no acceleration. Let's see what happens with the y. In this case, when I separate the variables out, our initial conditions were t equals 0, y dot was v sine theta, bit of integration, v sine theta minus 10t. Okay, there's my velocity vector. So v is that expression, and whatever the magnitude of v is, obviously it would be times that. All right, let's find displacement. So now, velocity I'm thinking of dx to t. Separate the variables, do it again. Integrate both sides, we get vt cos theta. Now let's do the y one. Integrate both sides, vt sine theta minus 5t squared. There is our displacement vector. By the way, you'll notice I've just put r and I didn't bother going rt. That's okay. You don't have to put the t in there. I mean, we understand t is the pronumeral in all this. Common questions that you get asked in projectile motion. When does the particle hit the ground? Okay, well, we know it's going to hit the ground when y equals 0. We're going to end up with these 3 sets of equations for the x direction and 3 sets of equations for the y direction. It's just basically picking out the right equation to use. So it hits the ground when y equals 0. What's the range of the particle? How far did it go? How could we solve that? Well, I'd have to find when it hits the ground. So I solve that y equals 0. That'll give me a time that it hits the ground, and I can substitute that now into the x displacement, and it'll tell me where it hits the ground. What's the greatest height of the particle? Well, what I know there is it'll keep going, but when it stops and comes back down, that's the key thing. It stops. It stops going up vertically. So it must happen when y dot is equal to 0. I'll solve that one. Then I'll substitute that into the actual y displacement, and that'll tell me how high it's gone. What angle does the particle make with the ground? So I like that one. Well, when it hits the ground, what angle is it going to make? Well, again, we'll have to find when it hits the ground, so I'll solve y equals 0. Substitute that into y dot, because it's the velocity vectors you use when you want to work out direction. And then, well, x dot's constant. We just can draw up ourselves a triangle. Right, there's the angle that it hits the ground. Some people insist on giving the angle to the positive side. Doesn't matter. You're saying the angle that hits the ground at 30 degrees or hits the ground at 150 degrees. Doesn't really matter. So to summarise that, what we know, basically that's it. That's all we know. It'll start off with a horizontal acceleration of 0, a vertical acceleration of minus g. That's it. Everything else we just then derive. So unlike physics, bad luck all you physics students, where you've got all these wonderful formulas that you substitute into, we don't bother with them. We don't need them. We just solve the maths. With initial conditions, and so fair enough, we can quote those initial conditions. We've got a pretty straightforward example. Ball's thrown in air, velocity 25 metres per second, angle, well, inverse 10 to 3/4 is what we've got there. Find its greatest height. Now, in order to do that, we have to create the equations. Now, a lot of times you'll now find in exams, they'll give you the equations to save you deriving them each time. And they'll usually put a big thing saying, do not prove this, or something like that. So if they don't, of course, well then you've got to derive them to use it. So let's derive them. So initial conditions of our problem. Well, there's what they told me, that it went off with an inverse tan of 3/4. I'll just draw up a triangle so I can work out what cos theta and sine theta are. I know horizontal velocity will be a constant v cos theta. That turns out to be 20 meters per second for this problem. And in the vertical direction, we end up with 15 meters per second. Okay. We start with the two accelerations that we know. So on the left-hand side, I'll change it to dx dot dt. It's pretty much the same as I just did in theory, but of course now we've got some numbers to put in there. So it'll be going from 20 to x dot, and we end up with x dot is that constant 20 that we were expecting. Over on the y's, and a bit of integration, and we get 15 minus 10t. Okay, let's now integrate again to get our displacements. So over there on the x, the horizontal is 20t, and vertically 15t minus 5t squared. Now sometimes they might say give the vector equation and things like that, in which case we then recombine it and go so much I or j, or a lot of times with these ones, rather than mucking about with the I and j, I'll just write it in a column vector and put the 20t on top and then the 15t minus 5t squared underneath. So it just depends what the questions are. Basically, we've now got all the equations. We should be able to solve our problems. And the one they asked us was greatest height. We know that occurs when y dot equals 0, so let's solve it. T equals 3 on 2. So it's after 1.5 seconds. Sub it into our y equation, 45 on 4. So there's our greatest height. Range. So how far does it go? The thing I know about this, because I have projected from the ground, then I know it's symmetric because it's a parabola. So if it just took me 1.5 seconds to get to the greatest height, it must take me another 1.5 seconds to hit the ground. So in this case, I can just go, oh, well, yeah, okay, time of flight's 3. Now, if I did not know that, then I would solve y equals 0 and come up with the solution. Remember, that only works when it's symmetric. Because I projected from the ground, that worked. So when t equals 3, x is 60, there's our range. Well, rather than when it hits the ground, let's find the velocity and direction of the ball after half a second. What happens after half a second? So we're going to need the two velocities, the horizontal velocity and the vertical velocity. That's what we use to come up with this answer. Well, horizontally, it's a constant 20. Y dot, we end up with 10. So let's draw it. We're going 20 and 10. They're both in the positive direction. That makes sense because we said it reaches the greatest height after 1.5 seconds. So after a half, we must still be going up. So we know the magnitude is 10 root 5. So we know the velocity. Direction, we've just got to find that angle. So obviously I've approximated, it's not an exact value. We get 26 degrees 34. So all right, I know after half a second, that's what it's doing. There's our example. We got close last